Hello everyone! This video demonstrates how to divide models into construction stages and explains about the multi-story feature in STRAP. Usually, a multi-story building made of reinforced concrete is built floor by floor, with each floor representing a new stage of construction. As a result, some of the construction loads imposed on a floor act without the presence of the floors above it during the construction, which affects the way forces are distributed in the building. For this reason, the multi-story feature has been added to STRAP. When using the multi-story feature, the software automatically divides the model to construction stages and adjusts the calculations accordingly, ensuring that each construction stage modifies the structure's static scheme. The application of loads on the structure adjusts according to each construction stage, and the results of each stage are combined in the final solution. For example, for a multi-story reinforced concrete structure, where each floor is cast step by step, it would be correct to load the self-weight of the elements based on that construction stage. To clearly demonstrate this principle, we will use a two-dimensional model of a 4-story structure with uniform floor heights composed of columns and beams. We will first divide the structure into construction stages manually, specifically based on its levels in this example. Click on Stages on the menu on the right to open a dialog box where you can define the construction stages. Click on Add to define the first construction stage. Name the new stage. Make sure it is based on the whole model. And click on OK. The program enters the editing mode where you can add restraints, edit sections, change the end conditions of elements, and perform other actions to define each individual stage. In this example, we will remove from stage 1 all the elements above the first level. Click on Beams, deactivate, and select all the elements above the first level. End the selection. We have now finished defining stage 1. Let's go back to the stages list and continue defining the rest of the construction stages. Click on Stages on the menu on the right. Click on Add to create a new stage. Name the new stage. Make sure it is based on the whole model. And remove all the elements above the second level. Let's go ahead and create stage 3. Click on Add. Change the name accordingly. Make sure the stage is based on the whole model. Remove all the elements above the third level. And end the selection. In this example, it's unnecessary to define stage 4 since it represents the whole model. We have now finished defining all the stages. To view the list of the defined stages, click on the Stages option. To make changes, click on a stage to return to the editing mode. We will now start defining the loads. In many cases, structural analysis involves applying loads to the entire model at once, similar to the load case depicted on the screen. This method can be inaccurate for certain loads, leading to significant discrepancies between the model-based results and the actual structural response. Essentially, as the number of construction stages increases within a structure, so do the discrepancies. To clearly demonstrate the impact of the self-weight of the elements on the structure, we will apply the load of each stage separately. Let's define a new load case for the first level. Name the load case. Select the model based on stage 1. Each stage represents the casting of a new floor in the model, so the load should be applied to the newly constructed floor in that stage. Repeat these actions for stages 2, 3, and 4. In the next construction stage, another floor is cast, but the loads from the bottom floors are not transferred to it. The bottom floors have already been subject to previous deformations and stresses, to which the next construction stage adds its own. The self-weight of an additional floor is redistributed between itself and the existing elements in the structure, and so forth. Effectively, when construction is carried out in stages, it changes the static scheme at each stage, influencing the structure's response to new loads. Let's define a combination, which includes the 4 stages we've defined. Click on Combinations, Define Combinations, create a new combination which factors all the stages, and solve the model. Let's present the moment diagram for each stage. As the stages progress, the bending moment diagram for the loaded beam clearly transitions from representing a beam fixed at both ends to one fixed at both ends with support at the center of the span. This occurs due to a change in the structure's static scheme as the stages progress, during which the central column develops a vertical resistance to the displacement of the beams. Similarly, as the construction stages progress, the stiffness in the structure changes, as shown by the decreased displacement in the center of the loaded beam. Let's present the differences in results between staged loading and global loading. Select the 4 stages combination we've defined before. Notice the differences in the bending moment diagrams between the floors. There is a significant variation in the values between the bottom and top floors, in addition to the displacement as mentioned before. By contrast, the structure subject to global loading exhibits similar bending moment diagrams across its floors. This disparity occurs due to the fact that the structure was loaded only after its construction was complete. As was explained before, the difference stems from the application of loads on different static schemes. When comparing the deflections between the load cases, the structure subject to global loading shows nearly identical deflections between the levels, similar to what is seen in the bending moment diagrams. The displacements of the nodes occur based on their initial positions before the loads were applied. In contrast, the structure subject to staged loading presents increasingly smaller deflections as the levels progress. But unlike the structure subject to global loading, the deflections occur based on the previous stage, meaning based on the levels below. When comparing the reactions between the load cases, the sum of the reactions is the same in both cases and equal to the total of the external load. However, there is still a difference in the reactions distribution, which is influenced by whether the loading is applied sequentially or simultaneously. Let's demonstrate how to use the multi-story feature, which automates the manual process of defining and loading the stages, as was presented before. In the Geometry tab, on the menu on the right, click on Stages. Click on Create to activate the multi-story option. A window will open displaying the division into stages based on the structure's levels, as was generated by the software. Remove stages from the automatically generated list by highlighting them and clicking on Delete Level. To add levels to the list, click on Add Level and select the levels in the model. At the top of the window, you can adjust parameters that influence the automatic level generation, such as the height direction, the tolerance, which determines the spacing between levels used to define the stages, and the time intervals between the casting of each level. In the Loads tab, let's define a new multi-story load case. Since we previously activated the multi-story option, the option to define the load based on the multi-story stages appears on the list. Apply the same loads on the structure as we've previously done. Now, with the multi-story function enabled, the software will automatically allocate each load to the corresponding stage, similar to the manual process we demonstrated earlier in the video. And finally, solve the model. Now, let's present the results from the multi-story load case. It is evident that the results from the multi-story load case are identical to those from the manual stages load case. The multi-story feature automates the process of creating and assigning loads to stages, as well as defining combinations. This greatly facilitates the process, particularly in structures with many stages. In conclusion, the multi-story feature is an important and user-friendly tool that can enhance the understanding of a structure's behavior, especially in complex multi-story structures with numerous construction stages. It should be taken into account that the calculation process may take significantly longer when analyzing large models with the multi-story feature. Additionally, utilizing the multi-story feature becomes increasingly significant when analyzing attributes dependent on time or stages, such as creep.